Well, good afternoon, and welcome to the Wrangling Complexity breakout session. I'm Nan Mattai. I'm Senior Vice President of Engineering and Information Technology at Rockwell Collins. At this time, I'd like to introduce the four panelists, starting with John to my immediate left. John is the Director of Focused Technology Roadmaps at Lockheed Martin Skunk Works. In this position, John is responsible for maturing and transitioning technology to address the needs of the aeronautic platforms. Next to John is Evan Fortunato. He's the co-owner of Apogee Research. Previously, he was director at BAE Systems and a program manager at DARPA. Evan's research includes adaptive and resilient cyber-physical systems. Next is Kathleen Fisher. She's a professor in the computer science department at Tufts University. Previously, she was a principal member of the technical staff at AT&T Labs and a program manager at DARPA. Kathleen's research focuses on advancing the theory and practice of programming languages. Finally, we have Richard Murray, a professor of control and dynamical systems and bioengineering at Caltech, and an elected member of the National Academy of Engineering. Murray's research is in the application of feedback and control to networked systems with applications in biology and autonomy. So, why are we talking about this topic today? I will set the stage for the discussions that are going to follow with the finalists. As an engineering leader, I'm often posed the question, what keeps you up at night? And what are the biggest challenges facing product development? And at the top of that list is designing systems that work on time, on cost, in an environment of increasing systems complexity. Now, for many of you in the room, I think you know that systems complexity is on the rise, and aerospace systems are among the most complex. Not only do we have to perform with precision, these systems also demand safety, security, reliability, and consistent quality. So, take, for example, the F-35. Lockheed Martin refers to this platform as a digital jet for the modern battle space. Rockwell Collins is very proud to have been the designer of the helmet-mounted display. Now, much has been written about this program in the news, but I'd like to share a little bit about the helmet-mounted display. It's truly one of the most advanced systems on the F-35. The pilot sees all the information necessary to complete his or her mission it's projected on the visor of that helmet. We like to say that the pilot is able to see through the airframe, which means that if the pilot looks down at the cockpit floor, he sees right through to the ground below him. Now, the development of this system has had many challenges. Over the years, and you may have read about some of these, we have had setbacks and cost overruns. We have struggled with performance issues, and actually things got so bad that in 2011, the Pentagon contracted with BAE Systems to develop a backup systems just in case we could not work out the kinks of the system. Well, fortunately, 4 years later, we have, and we just delivered Gen 3 of the systems to Lockheed Martin, which has largely resolved many of the problems. But this is just one example of the complexities that we deal with day in, day out in aerospace product development. Now, I'd like to share some quotes with you on this topic. And the one that I call your attention to is the one in red by Dr. James Truchard, co-founder of National Instruments. He was writing an article for the Society of Automotive Engineers and commenting on the pace of increasingly intelligent machines. And if you notice in that quote, he commented about keeping pace with rapid evolving complexity and the need to evolve methods. And that's what we're going to be talking about later today. Finally, another industry that has been seeing similar trends in complexity is the automotive industry. Cars are no longer only a mode of transportation. Actually, we think of them and purchase them today like tech devices. Back in the 1950s, all it took was a mechanical engineer to bring a car design to fruition. Today, many vehicles are heavily computer-controlled. In fact, the low-end vehicles can have as many as 30 to 50 electronic control units. And as you can see, they have typically about 10 million lines of code, software code. The higher-end systems can have as many as 100 million software lines of code. Now compare that to the F-35 with 8 million and the Boeing Dreamliner 787 with 14 million. Just think about that complexity. So, as we look ahead, to stay ahead and to build the systems of tomorrow, I believe we have to do two basic things to survive. One, reduce the complexity, and two, improve the complexity that remains by leveraging modern design practices, modern tools, and technologies that would help us to deal better with complexity. So that's what the panelists are going to share today. So I'm going to turn it over to John Clark to share his perspectives on this topic. John.
Thank you, Nan. So when we look at complexity as we move forward with the aerospace part of the industry, being a part of Lockheed Martin Skunk Works, we're continuing to see an evolution in the capabilities that are being further decentralized in the platforms. And so as you look at our airborne systems, there are an increasing amount of capabilities that are being pushed to the edge. And it's not just pushing those capabilities to the edge, it's those capabilities actually communicating with each other at the edge. And as a result of things, you look at these levels of complexity and the interaction happening between the systems, increasing at very significant clips. Right now, we still have the issues that permeate with communication of this information and ensuring that each of the individual nodes receive the information that are necessary to do their different types of jobs. Within an F-35 force ship, there's a clean and clear-cut way in which information is communicated. However, moving that information from an F-35 to a B-2, moving that information to an F-22 or any of the other platforms creates another problem in which you want those systems to interoperate with one another, yet there's very limited ways in which the information can be communicated. As we break down those barriers and that information is able to be communicated, you then have the issue or concern of how that information can be adversely impacted, or you have denial of that information, which is critical to do some decentralized operation. And so as you look at these different activities, as you're trying to operate in an A2AD environment, it puts a situation where not only are you dealing with a lot of software at the edge that's having to consume all this information and make decisions from this, you also have human decision makers in that process that have to understand what those decision algorithms are, why they made those decisions, and from that information be able to quickly determine whether the machine made the right decision or whether the machine needed to take an alternative course of action. And so that union of information and the complexity being computed at the edge with the human interacting with that information to ensure that the right decisions get made creates a very tough problem for all these different systems to interact and work in a multimodal way. So as we've been going forward, there's been a number of different ways in which we have tried to attack this problem. And so, there's the typical example of highlighting Lego blocks, and I use that as just a simple characterization of managing complexity because you have very well-defined interfaces, and with these different composable units, you have a number of ways in which you can build different items. However, when you look at the way in which we've done standardization in the past, we've developed a standard. That standard becomes very rigid, locked in stone, and as you go forward, there's limited to no way to modify or update that standard in such a way that the systems can actually, transcend time. And when you have systems that on the aerospace side are still out there 50 years ago, from 50 years ago, you got a B-52 still in the inventory doing great things. However, the way in which you interoperate with that and the way in which you'll interoperate with a B-2 in the future are two very different things, even though you're doing the same type of mission. And so you've got this problem where this complexity not only is an instant in time, it has to transcend time as you're working through things. So what ends up happening with these systems is you end up with very unique interfaces because the technology that was developed for a system today is not the same technology that will get developed for a system tomorrow, and this is further exacerbated by the fact that it takes us so long to field systems because of the DoD acquisition process, coupling with requirements and the testing and everything else that goes with getting a system in the field. And so when you have these unique interfaces and then you're trying to figure out how to put things together, a lot of the information needed to do very complex activities, it's not available for the other systems to consume. Something as simple as just knowing where another aircraft is in space such that you can make an actionable decision is not readily available. You have to jump through lots of wickets to find that information, and it becomes very problematic to getting capability in the warfighter's hands. So as a part of a series of Air Force-related activities in the 2005 to 2007 timeframe, there was a look at how you could start to standardize things and go more toward that Lego block mindset. One of these specific efforts was the Unmanned Air System Command and Control Initiative or Interface, or UCI as you more commonly hear it referred to. The whole intent of this activity was to work towards standardization of the complexity within a ground station and how these different systems could interoperate with one another such that if you're consuming weather information, something as trivial as weather information coming from AFWA, that there's not multiple implementations of that interface in order to be interoperable with the AFWA data. That further grew into an activity called Open Mission Systems that looked to take that same sort of mindset and put it onto an embedded system inside of an aircraft and then use that as a way to separate hardware from software and put that capability of interoperability down at the sensor level so that that data was readily exposed to the network. So these types of concepts of being able to have these disparate systems work together could be made to occur. The Navy has followed suit with some of their own activities. There is, between the UCS effort, the Navy interoperability profiles, as well as FACE, there's a number of standardization efforts that are attempting to find a way in which we can get some sense of interoperability amongst this complexity. Now, the challenge with this is that just as we've seen in the past, whether it's STANAG 4586 or whether it's Link 16, these standards become very rigid, and we need to live in a world where we're able to adapt to the complexity as we encounter it. So as we start to put these systems together, we have to ask the questions, how will these systems be controlled? Who's got the authority to control these systems? As we expose a sensor to the network for anybody to interact with, who gets to make that adjudication that is actually the right person to control it or the right piece of software and it's doing it for the right purpose? And how do we verify or trust that the data that we've been given for an external command is actually trustworthy to move through it? And then as we're exposing all this data to the network, can the network actually handle the load that we put on it? So as I mentioned, we can't become beholden to the standard. We have looked at Link 16 and STANAG 4586, and those are even legislative mandates to use STANAG 4586 in some cases. But the challenge is you go look at STANAG 4586 and the types of interoperability or the types of command and control activities that you may want to perform are extremely limited given the framework that's been put there. Now, it would be great if you could simply say, you know what, I need to add this content or this message or this set of fields to the standard and it show up a couple of weeks later and actually have some agility to it. However, you look at the ratification process that goes through for these standards and you end up in this state where you actually end up stifling your innovation as a byproduct of sticking within the confines of the standard. So that lack of flexibility drives you down two paths, either a very limited system or something that becomes very unique again, and the standard interfaces go by the wayside, and you don't really have the ability to have that interoperability and have these system of systems work together. So the trick with all of this is trying to find that right balance. With the Open Mission Systems activities and the UCI message set, one of the things that's, the simple characterization of that is that it's working to try to find the standard language between all these systems, but it's not necessarily addressing the unique dialects that may exist within the language. And so as a result of that, there are a number of things that we're continuing to do to explore how we can take something that has some standard benefit that gets you a lot of the upfront interoperability started. However, then looking at how you can verify that those components or as you adapt the standard continue to be put together properly. So one of the DARPA activities that Dr. Sandell alluded to earlier in the day is the SOCITE program. With this program, it's looking at how not only can these standards be leveraged as we go forward, but systematically through the technology, they can start to become very agile and almost atrophy over time as the technology and the innovation moves forward. So specifically, there's capabilities with the cybersecurity where we're looking to ensure that the source of the data has the root of trust associated with it so that you can ensure that the right data is coming from the right source at the right time. As we start to get these building blocks and expand that Lego metaphor, how we verify the composition of these systems as we start to put them together. And so the idea that we now have this new system of systems capability, that the way in which we use those systems today can be composed different than we use them tomorrow, and that flexibility gives us the ability to put new capability in the field much faster. And then that last piece of that is really that adaptability, so that all of these different components facilitate new warfighting capabilities rapidly. So, the SOCITE program is instrumental in trying to find that balance between the systems. And as a byproduct of that, there's a lot of emerging technology that I'm going to hand over to Evan to talk about specifically in those areas.
Thanks a lot, John. Good afternoon, everyone. Today I'm going to be talking to you about composing systems without common interfaces, which seems like a little bit of an odd thing to try and do in the first place. Let's dive right into the next slide and try and understand what is the goal we're trying to serve here, which is composing systems that keep up with the times. Now, this isn't something we normally think of the DoD being very good at. In fact, the DoD takes an opposite opinion. They want very predictable, homogeneous, fixed configuration systems, so they know how they'll respond. They know how they'll act 30 years out. But the reality is, meeting 30-year-out requirements with today's technologies is darn near impossible. And so the result is we get these fantastic designs, but with 20 to 30-year-old technology. And those designs can't evolve. So that doesn't really work particularly well. And the government knows this, and so they've made a number of initiatives, like the open architectures that John just discussed, to try and address this. But there are issues with that as well, despite the strides it's made. It requires enormous effort to get consensus. And once you've gotten the consensus, you certainly don't want to go back and renegotiate it, so it becomes stuck in stone. For every global consensus, there's a bigger global. So it's really just a local consensus. You get the Air Force on board. What about the Navy and the Army? You get the DoD on board. What about the intelligence community? You get the whole US government on board. What about NATO? It never ends. There's always the next interoperability frontier. That complexity remains. So the question then becomes, even if you've got the global standard, is that really helpful? And the reality is, if the standard is everything to everybody, it's not what you want for your need. And we've all experienced this, living in a bureaucratic environment that's serving everyone else's need, but not your own. It's not much fun. So the result is, in the best case, that we get heterogeneous components. We can change those Lego bricks out, but in a completely homogeneous architecture. And as the technology changes, we need to change the architecture. And so we try and anticipate the technology revolutions and put this sort of adaptability into the architecture. But anticipating technology revolutions is pretty much a fool's errand. And so we just end up with more complex systems that don't really work for even today's problems. So this isn't working. This doesn't seem like a very good path. Let's take a step back and ask, can we achieve the underlying goal, interoperability, without needing a common interface at all and just get rid of all of these problems? Seems a little crazy, but let's go through it. So what is the underlying problem that's causing this issue? And it's getting systems to understand one another. So I'm going to use a DoD application here because we're DARPA, but at a DARPA conference at least. But you can imagine commercial applications just like this. So you've got two communities, let's say the Air Force and the Navy, and you've got systems in these communities. And some of the Air Force systems can talk to the Air Force, other Air Force systems, and some of the Navy systems can talk to other Navy systems. And there might even be a few really outgoing systems that can talk across the boundaries, like the Distributed Common Ground Station, DCGS. You think with a name like Common Ground Station, it would be common, but of course it's not. All right, so now you need a new link, something very reasonable, like your Air Force UAV needs to provide data down to your Navy carrier group. Seems reasonable, seems like that should be an easy thing. But you can't anticipate every interface you're going to need, so you don't have that one. What do? Well, right now, you can go through an acquisition and spend multiple years and millions of dollars and get that one link added, but at that point you probably need a different link because you've got a different UAV. The old one's not really that relevant. You could relay all the data through the existing system, send it down to the ground station, send it to the Air Force DCGS, send it to the Navy DCGS, then out to the Navy carrier group, but that just seems like a silly waste of resources and adds all sorts of latency. Neither of these make much sense. So is there a better way? Well, as computer science does all the time, there is a better way, and it's abstraction and recomposition, but with a slight twist. So many people have tried to abstract interfaces, but that's very hard. To understand what part of the semantics and the syntax of the interface is important, it's unknown, and it's a priori can't be known because it's going to change. So instead of trying to abstract the interface itself, what if we tried to abstract the transformation between interfaces? So that's represented in the colored lines of these diagrams. So for instance, if I've got data in an Air Force UAV format, representation, and I want to convert it to an Air Force ground station representation, that yellow line does that for me. Yellow arrow does it for me. I don't know how it does it, and I don't really know what it does, but I know it does that. I can do the same thing for the green line and the blue line and the purple line, and now a very fantastic thing happens. If I combine the yellow transformation on the green transformation on the blue transformation on the purple transformation, I put Air Force UAV data in, and out pops Navy carrier group data. Even though they're not a common interface, I don't even know what that composed transformation is. Computer does, but I don't. And the two organizations, the Air Force UAV and the Navy carrier group, have never negotiated an interface or a transform between their interfaces. Well, how did that happen? Now, of course, we need to represent this information, and we need to represent it efficiently, and whenever you want to represent some complex combinatorial explosion of options in a compact representation, you use a graph typically. I guess there are other options, but I like the graphs. So as with all graphs, it's got nodes and links. The nodes capture the field information, the basic structure, and the properties of that field, but it does it in a completely local way. I use my own time, I use my own space, Nils uses his own time, his own space, and that's okay. There's nothing wrong with that. We don't have to negotiate. Now, the links are the interesting part. The links capture the differences between pairs of interfaces, but I don't need to go every pair. All I need is one path, winding as it may be, through the entire graph. And now I can chain those up to reach any other system. So let me walk you through the specifics of what this approach allows, because there's quite a few things come out of this very, very simple change of perspective. A lot of the complexity just melts away when you look at it in this way. First, by capturing these differences, instead of capturing the interfaces themselves, we can create these transform chains and create optimized interfaces for this exchange, not worrying about what everyone else needs. That doesn't matter. It's efficient and on demand and very quickly generated. So that's great. That's that interoperability without a common interface. But if you remember, the original goal was more than that. It was making systems that evolve with the times. So now I want to change my architecture. I want to add a new system which has got a new interface. Well, it turns out it's very easy to do that. All I need to do is connect that new interface to any other node in the graph. And once I've done it, I can borrow everyone else's transform definitions and reconstruct any other transform to any other place. Well, if I can add one node to the system, could I take two communities, each of which had a set of protocols interfaces, and make them work together? Normally, this is the bane of interoperability. I've got the Air Force and the Navy, and I have to do 1,000 transformations to make this work. Here I take one node in the Air Force, a particular popular node, one node in the Navy, and I bridge them together with a new transform. Once I've done that, I can take any node in the Air Force, follow it to the bridge node, hop across the bridge node to the bridge node in the Navy, and then follow it to any other node in the Navy. So by adding a single small set of links between the two communities, I've now created an interoperability between a large set of heterogeneous interfaces in each community. This has astonishing implications. Now, instead of having to have everyone go to the same interface standard from the beginning and get locked to it, everyone can develop on their own interface standards. And when it's time for interoperability, with a small amount of effort, you create the interoperability that you need. Finally, by capturing the properties, again, in this local way, I don't need common agreement on how to capture the properties. I can automatically reason over the behavior of the system in the local frame. It's different everywhere, but it's still doable. And that allows me to do enforcement of security policies. So the systems are doing what they intend to be doing. Now, this is a different approach, and so it requires a little different set of tools. But many of you will recognize that these tools are actually very well-known tools in other disciplines. So first, we need a design space exploration that lets us automatically search the synthesis space. For instance, there may be multiple paths through the graph. Which one is best for your particular application? Second, we need some way to instantiate this concretely. That looks a lot like a domain-specific compiler out of the computer science community, where I can automatically instantiate an optimized, concrete version of that interface that does just what I want, just when I need it. And finally, we need some basic estimation and control techniques to enforce those properties that we put in to ensure the security properties and that we have some confidence that the system is going to behave the way we expect. So with that overview of a slightly different way to look at this problem, I'm going to turn it over to Kathleen, who's going to talk about hackums and computer science and how that applies.
Thank you. Thank you. Right, I'm Kathleen Fisher, and you might think of me as an ambassador from computer science space, speaking to systems engineers. So my background is in computer science. Computer science deals with complexity all the time, although it's a slightly different form of complexity than what system engineers typically cope with, in that the complexity in computer science is typically arising in synthetic systems, right? We make our own nest, our mess, and we have to deal with that. So the graphs on the slide here show some measure of the complexity of a particular system, the Linux kernel, which is an open source project contributed to by volunteers around the world. The top graph shows over time the number of commits to this repository from 2005 to 2014. The last couple of bars show that the number of annual commits is over 70,000, which means that essentially every day there are more than 200 people making changes to the source code repository in a very distributed way. So there's not a single authority who's checking everything. It's this distributed process that's managing this complexity. The graph on the bottom shows the amount of code that these people are working on. Horizontal axis is time, the vertical axis is lines of code in scientific notation. So the bottom left hand is 6 million lines of code, and the top is 20 million lines of code over a period of roughly 9 years. So what is the approach? How does computer science cope with this kind of complexity? So researchers actually struggled with this quite a while in the 1970s and the 1980s, and the ideas that they came up with are composition and abstraction. So the idea is you develop a particular building block, like in this case it's showing the STO4 microkernel, which is a microkernel which allows you to, if configured properly, run separate processes and manage the communication flows between those processes in a way that they get the resources that they need from the computer, from the underlying hardware, and they can't interfere with each other. So the system has a couple of interfaces. Interfaces at the bottom are things that that particular software module depends upon. Interfaces at the top are things that depend upon this particular module. And then within the scope of those interfaces, the people who are working on the STO4 microkernel are free to make whatever changes they like and know that the rest of the system, in some sense, isn't going to care, so that they can make those changes independently of all the other changes in the system. Now, some interfaces are better than others. The interface at the bottom there is a hardware interface, and so lots of details about the underlying chip actually kind of leak through, which means that porting the STO4 microkernel from one processor to another actually requires some amount of care and attention to detail, and you have to change some stuff. The interface at the top, however, is a really clean, beautiful interface, which means that lots of different kinds of software can be layered on top of it without having to change that microkernel at all. And that the microkernel can be reused in lots of other systems. So that's the basic notion of abstraction, and then composition allows us to build more complicated systems by putting these independently built and maintained systems together. So this particular architecture here is the architecture that the HACMS researchers have used on the quadcopter and the Boeing unmanned little bird that they've been researching. The goal of the HACMS researchers would, with relatively little amounts of resources and time, build software for those two vehicles that red teams wouldn't be able to break into and hack remotely. So for example, the mission computer on the right is running the SE4 microkernel with glue code on top of it, running mission control software, directing the unmanned little bird or the quadcopter where to go, what to take pictures of, things like that. One of the partitions in the SE4 microkernel was set up to run Linux, and on top of that, the red team was able to run whatever code they wanted with root access. The other computer is the flight computer that's running the eChronos RTOS and running flight control software that does things like stability control and hovering ability, things like that. So like the eChronos RTOS on the left-hand side similarly has interfaces like the SL4 microkernel did, and that allowed the researchers to swap out the eChronos RTOS and put in the free RTOS when the eChronos RTOS wasn't ready in time. So basically these tools of abstraction and composition are how computer scientists build complicated systems out of simpler pieces. Each one of those boxes is shown as kind of a unified block, but in fact each one of them inside has separate components with interfaces together so that you can end up building a very large hierarchical system by dividing it into these pieces. Of course, not every property can be divided up into individual pieces, and so the other kinds of properties, the ones that lead to emergent behaviors, have to be managed separately. These things are like feature interactions that come up in the telecom industry, security properties, which is one of the reasons why they're really hard to manage, and resource utilization kinds of things, so properties related to time and space. So computer scientists often deal with these kinds of resource properties by wildly over-provisioning the system, making sure that it's way fast enough so that it can make any timing deadlines and has plenty of memory so it won't run into that. Situations, software that's more tightly constrained, we have to reason more carefully about the code, and computer scientists have developed tools to help deal with those kinds of situations. So for example, this slide outlines 4 different kinds of classes of tools to help with these kinds of properties that are not captured in interfaces as well. These tools range in level of effort required to use them and the strength of the guarantees that they provide. They range from tools like Rockwell Collins Agree tool for managing assume guarantee reasoning. Now what does that mean? So the property that Rockwell Collins wanted to establish of the HACMS quadcopter and the unmanned little bird was a security property that said that only authenticated messages would be acted upon when they're received by the quadcopter. So some hacker couldn't send a message to the quadcopter and tell it to fly off into the sunset, for example. Now that's a property of the entire system. It's not a property that you can chop up and prove the same property of all the component pieces and expect that to make sense. Instead, what you have to do is take that global property and break it up into properties that are specific to the underlying components. Each one of those properties is written in a form where it says, well, if the environment provides all of these guarantees, then I will provide this guarantee back to the environment. You take each one of these blocks and you put it all together and you show that the conjunction of everything that everybody assumed establishes everything that everybody guaranteed, and therefore you get that system-wide property. Another kind of tool is a model checking tool. So model checking at the highest level of abstraction allows you to build a model of your system and properties, and then model checkers very smartly search the space of all your possible models to check to see if any of them violate that property. Researchers at Microsoft showed how to apply that tool when the model wasn't some abstract mathematical thing that was in Simulink, say, but the actual real code that was running on the system. The reason why Microsoft cared about this was because they were getting a lot of really bad press because of the blue screen of death, right? Your Windows computer would crash and you would blame Microsoft. But in fact, it was almost always the device driver's code that was at fault. And so what Microsoft did was adapt the software model checking technique so that they now required their device driver code to pass this model checker. And only if the model checker said that the code was okay would Microsoft then allow the device driver to be bundled with Microsoft software. And as a result, when was the last time you saw a blue screen of death? Right? I haven't seen one in a really long time. They still happen, but much more rarely. So this tool was allowing them to be able to check emergent properties of the device drivers in a way that mattered for the whole system, the Microsoft code plus the device drivers. Another kind of formal methods technique is based on static analysis, which is analyzing the code for properties that you're looking for. This kind of approach tends to be less labor-intensive, more automatic. So, for example, Facebook has just adopted the Infer framework, which allows them to analyze millions of lines of code in Facebook Messenger apps overnight to be able to automatically detect and prove the absence of null pointer errors and resource leaks. Right? This is proving properties about a resource property, so one of those kinds of properties that is not easily captured in the interfaces. And then at the extreme end of level of effort required being high, but also level of assurance, level of knowledge of the system being also extremely high, are interactive theorem provers. So interactive theorem provers are the technology that the research lab in Australia called NICTA used to prove that the SEO4 microkernel was fully functionally correct, which meant that it did exactly what it was supposed to do and nothing else. And it's that high level of assurance that the HACM's researchers were able to leverage to build a system on top of it that established the security properties that the HACM's researchers were looking at. Now that SEO4 microkernel is only 10,000 lines of code, which you say is like, that's super tiny level of code. And that's true, but the idea is that you can leverage that small amount of code to be able to build guarantees over a whole system, and you don't have to prove all of the code in the system to the same level of rigor. So in fact, that's what the HACM's researchers did. At 18 months, they flew the SMACM copter, which was the toy quadcopter that had open access so all of the researchers could see all of the code. Nonetheless, it had about 75,000 lines of code in it. It had stability control, altitude hold, directional hold. It had denial of service detection. It had about 80% of the GPS waypoint navigation in it. The Rockwell Collins team and the colleagues were able to prove that the system was memory safe. It ignored all malformed messages. It ignored all messages that weren't authenticated. All received good messages were actually executed on. And the red team was able to get full access to the source code for 6 weeks. And in that time, they were not able to break into the quadcopter or disrupt its performance in any way. So my colleague at DARPA, who is a penetration testing expert, his assessment of the quadcopter, this quadcopter, was that it is the most secure UAV on the planet. So they've had 18 more months, and in that 18 months, they were able to port the code to Boeing's unmanned Little Bird, and they had a live flight test 18 months earlier than scheduled. The test pilot reported that the unmanned Little Bird flew exactly the same with the high assurance code as it did in the non-high assurance version, which is exactly what you want, right? You don't want the high assurance code changing the flight pattern. And they gave the red team a partition on the mission control computer where the red team had root access in that. So this is like inviting your enemy in. It's basically putting them on your platform and saying, do what you can. Of course, they didn't do that during the actual live flight test. They did this in safer conditions. But in that situation, the red team was not able to break out of their partition, and they were not able to disrupt the simulation of the vehicle at all, right? So that's the strongest, that was the result that the correctness proof claim should hold, and the red team experiments to date support that claim. So with that, I will happily pass it to my colleague, Richard Murray.
Great, thanks, Kathleen. So my name is Richard Murray. I'm a faculty member at Caltech, and I'm going to talk a little bit about the role of control theory and how that might help as we try and wrangle with complexity. So let me say a little bit about control theory as a discipline. So what is control theory? So the kind of standard thing that we teach, and if you've taken a class in control systems at some point, you probably saw a diagram that looked roughly like this. Right? The idea in control theory is that we use feedback to interconnect sensing, computation, and actuation to achieve some purpose. So if you're trying to regulate the speed of an autonomous vehicle, or you're trying to regulate the processing conditions of a chemical plant, or you're trying to regulate control of traffic across the internet, you need to sense what is the current situation, what's my current speed. You need to compare that to what you'd like to be doing, sort of check against the conditions, and then do some computation and say, okay, I'm going too slow, I'm going too fast, what should I do about it? And then actuate the actual physical system. And control systems combine many things, but I think that the four words that I would use to talk about them are the notion of dynamics, uncertainty, feedback, and feed-forward. Those are kind of the elements that compose a control system. And this is 50 years ago what control theory looked like, and this is the type of thing that the field has done. And this is used, of course, in modern aircraft and all sorts of process control plants. All of those sorts of examples use these, and you already heard from Kathleen, for example, the role that sort of inner loop plays down in the HACM's aircraft as an example. But this is sort of the traditional view of control theory, and I think control theory is starting to change a little bit. A little bit more modern view would be that control theory is a collection of tools and techniques for analyzing and implementing complex systems. And this is not a line that I put together for this particular presentation, but rather one that I use all the time. This is actually what we think about. It's a tool. It's not the only tool, right? You got to combine it with all of the things we've been hearing about. But we can really think about the role that feedback plays and the types of things that we can do. And so on the right, you see some of the more modern applications of control theory, from thinking about things like Mars rovers and autonomous vehicles to how cells work, to thinking about the internet, and the bottom pictures of battle space management system. And these are the things that people have been working on, and DARPA has been very much supporting in terms of control theory and the development of that. And I think that there are three key principles that I like to fall back on and sort of say, what are the principles of control theory and feedback control theory in particular? One is that feedback is a tool for managing uncertainty. If you have uncertainty someplace in your system, feedback is one of the tools that can help you manage that, and I'll talk more about that. The other is that feedback helps you design the dynamics of the system to be what you want them to be. And so if you have, for example, on the lower left, that forward swept wing aircraft, that's of course an unstable aircraft, right? If it tilts up a little bit, it goes unstable. But you can design the dynamics with a feedback system, right, so that it becomes a stable aircraft that a pilot can fly. And the last, which is very important and particularly important in the context of wrangling complexity, is thinking about the role of feedback in giving you component and subsystem modularity. That is, that making it so that that component with a feedback loop around it is something that can deal with different things at its inputs and outputs, right? That as you integrate it in that stack, either horizontally or vertically, that it adapts its operation to provide the same properties at its interfaces that you have designed the system around. So there have been a lot of advances in control theory over the last decade. And so if we really look at what some of those trends are and where people are going and where, if you're thinking about complex systems, the underlying technology may be there, I think there are a couple of things that have happened that are different maybe from when you last took your class in feedback control systems. So one is just the role of optimization-based control, in particular online optimization-based control. Computation is now at the point where we can do the sorts of optimization that we used to think of as an offline computation online in real time. So we can plan out a trajectory for the next 10 or 15 seconds of an aircraft, right, and then do that for a second and then reiterate on it. Right? And so the picture on the right is actually a program that was sponsored by DARPA as part of the software enabled control program, in which we were running real-time trajectory generation at 100 hertz and actually planning out what to do for the next 10 seconds and just rerunning that with a model of the aircraft. Now, why is that important? Because if the aircraft changes, you can change the model and redo the optimization. Or if an actuator fails, you can say, oh, okay, I have a different system. Or if your goals change, your mission changes, right, you can change that, and online your system will adapt to that. So computation, like every place in technology, has affected control theory as well, and we can now do these sorts of online optimization-based control in increasingly complex systems, right? And so aircraft are certainly one of them. The other is layering architectures, and you already heard about this from Kathleen's point of view as a computer scientist, but it's also affecting how we think about design of control systems. So the picture is the electrical grid, and the electrical grid has a number of different layers to it, right? There's the generator control, where you're actually just trying to control the phase and the voltages and other things, but there's also control that's happening at the next higher level, at the distribution level, and markets that are controlling, and all of these are feedback systems, right? They are sensing what's going on and reacting to those things, and it might be that they're implementing their actuation through price and then the way that people react to prices, or it might be that they're implementing that actuation by looking at, how much more power should I put to the generator, right, to generate the electrical current that keeps the phases right. So those layers and those abstractions are incredibly important, and you want feedback at each of those layers, right, as you put these systems together. Another thing that's happening is the role of formal methods, and again, Kathleen talked about some of this in computer science, things like model checking and theory proving, and I think traditionally the computer science community has developed those for situations in which there's not necessarily a dynamic system underneath, but when you look at cyber-physical systems, then you start having dynamics coupled with your computing system, right? And so the cyber part coupled to the physical part. And formal methods and the ideas from computer science properly adapted to those systems are making a huge impact in control. And so this is something that over the last decade or so, again, very much funded by and kicked off by a lot of DARPA programs, have started to do. The picture there is an electrical power system for an aircraft. That's one of the systems that you want to be incredibly robust, because if electrical power goes out in an aircraft, that's it. All right, we're done. All modern aircraft. And so the complexity, certification for that is that the software that's controlling that has to have no critical failures in 10 to the 9th flight hours. So 10 to the 9th flight hours, 100,000 years. All right? So if you fly an airplane for 100,000 years, you should have a critical software failure. Critical means loss of life. Right? So, but if you look at the number of aircraft that fly in the United States in a single year, that's about 30,000 flight hours, right? So in 3 years, you will use up, right, 100,000 flight hours. And so you actually use up a lot of that time very quickly. So in about 3 years' time, you go through that, right, because there's so many aircraft flying. So those levels, and if you think about it, right, across the world, you do see problems that come up at about that frequency, right? So we probably need to go more than that. And one of the ways to do that is to use formal methods to make sure, as Kathleen talked about, that there really are nothing that can go wrong, right, that you really have that guarantee. And a big one, and this is what people are trying to do, and of course, again, this cuts across many different areas, is how do we go from control and feedback around the components to control and feedback around the systems to control and feedback around the enterprise, right? So when you look at a battle space management system, that is a system of systems, right? And so what does the feedback look like? Where's the uncertainty? What do you want the dynamics to be? How do you apply these principles to that class of systems? Okay, so where can control theory help wrangle complexity? One is this idea of management of uncertainty. And so I've used here a very simple example, which is a electronic amplifier. And the thing about electronic amplifiers is that the individual components, in particular transistors, are not particularly accurate, right? You might get a factor of 2 differences in gain between one batch of transistors and another, especially in early days. And yet, if you go look at an electronic amplifier, you go take your iPhone, you dial it up to sort of volume 32, on all of your phones of the same model, it will be almost exactly the same, right? How do you do that? Well, you use feedback. You use precision resistors and other things that can measure what the actual output is and compensate for the uncertainty inside, right? So by measuring the output, seeing whether it's what you want, and knowing what direction to move things, and then recalculating, right, that feedback idea, you can provide robustness to uncertainty. Another is the design dynamics. And I mentioned this forward swept wing aircraft. This aircraft is such that the timescales are, it will depart before a pilot can correct for it. So if you were to fly it with the control system off, right, a pilot would not be able to fly this system, right? So we redesign these unstable dynamics to be stable dynamics. And again, we do that by making use of the ideas of feedback to design those dynamics. You tell me what you want the dynamics to be. I would like this to fly like the following type of aircraft because that's what I'm used to flying. And then use the feedback control system to give you those dynamics. And then the last thing, which is in some sense a corollary of the first two, is this notion that we can maintain modularity. And so if we want to maintain these input and output properties, right, we want to maintain an abstraction. This system should give me a certain constant gain from the input to the output. This system should do a certain operation in a certain amount of time, independent of sort of what's connected to it on the input side and the output side, independent of potential failures or changes on the inside, right? Maintaining that abstraction allows us to build these complex systems. And again, feedback is a tool for helping maintain modularity, right, and enabling these sorts of design abstractions that allow us to hide what's going on underneath, right? And that's an important concept, again, that computer scientists use all the time, right? The notion of abstraction to hide the details so that I can reason at my layer and worry about that. And I think feedback control can help there. So, thank you.
Okay, so we've just heard a number of very interesting and diverse approaches being discussed to handle complexity. From John, we heard about finding the right balance around standardization. From Evan, we heard about recomposing systems, potentially using graph structures. From Kathleen, we heard the computer science way, abstraction and composition. And we just heard of, from Richard, on control theory. What I'd like to do before opening it up for Q&A is to do a poll of the audience. What is the level of experience around this topic, complexity, systems complexity, within the audience? If it's high, raise your hands. Okay, medium? And low? Okay, so we've got a blend of different levels of experiences. My second question is, to get a sense of the audience makeup, which organizations do you represent? Are you from academia? If you are, raise your hand. Are you from government? Okay. And are you from industry? Okay, so here again, we've got a nice mix of the three. So as we set up for Q&A, as you can see in 2 of the aisles, there are mics that are set up. And what we'd ask you to do is if you have a question for the panelists, could you come forward to the mic and we'll take your questions. So to get us started, I have a question for the panelists. Over the last decades, many technologies have been researched and developed to deal with complexity. And examples would be things like high-order languages. Kathleen is pursuing research in programming languages, and high-order languages is definitely one of them. Open systems, and we had John talked about open systems architectures. Agile technologies, model-based development, and there were many others. From your standpoint, which of those technologies you believe has made a significant impact in helping us to deal with complexities? And which one do you believe has not really met expectations? And we'll start with John.
Lucky you.
All right. So I think that if you go back and look at literature, this will sound somewhat self-serving, but you go back and even in the early 80s, there is a lot of talk about open architectures and the employment of open architectures. And in my estimation, it really hasn't been until the last decade that there's been some significant movement with open architectures. And I think it's been the confluence of increased processing capacity coupled with the greater ability to move data around. And by doing that, we've been able to really transcend those limitations that existed in the past. Quick and anecdotal example, you got 1553. You can move a whopping total of 1 megabit per second across a bus with 1553, and you're doing it in a very constrained implementation that's, once again, you're beholden to a spec. With the way that the technologies have advanced now, you're moving a gigabit or more of data across Ethernet or fiber channel or any of the other emerging standards that have really given the opportunity for exposing this information because the network allows it, as opposed to in the past, we were hunting for that last bit to try to get something to fit on a wire, whereas we no longer have to do that. So I think that the open system side certainly has made a lot of progress in the last decade. As far as technology that really hasn't made any big leaps, I'll say that I've personally not seen a lot of advancement in the advanced programming languages that deal with these types of complexities. C++ is still the latest and greatest language, and that was the latest and greatest language in the mid-90s. So I've not seen a lot of growth in that area.
All right, so I'll definitely agree with John that open systems is probably the one that's had the most impact in operational systems, but I'll flip it on the other side. The one that I think is the most important from a looking forward perspective is the domain-specific languages. It's the ones that have changed our ability to handle complexity and handle it efficiently, where we don't have to basically go to de-optimize global systems, but we can actually get the same performance, but get it on a case-by-case basis. The domain-specific languages and the associated compilers are the ones that are most significant strides there and have come the furthest along. 20 years ago, this was not something you'd ever do, and now you download some open source packages, and it's pretty easy. 2 months later, you've got your own DSL and your own development environment, and you're compiling away. In terms of the ones that's most disappointing, I'd probably have to say model-based. There's a great opportunity there, but it always seems to be that you get the model wrong, and the refinement of the model is chasing the game forever, and as the system, refining the model takes almost as long as the time scale on which the thing you're modeling is changing. And so I think that would be the one that I'd pick for the second case.
Are there any thoughts on that question from the audience? If you do, could you raise your hand? And there's a free mic over there. In the meantime, I happen to agree with both John and Evan in that open systems has probably made the most progress. And I think while model-based development holds a lot of promise, I think its scalability, the maturity of it, is still out in the future. Are you going to comment on the question? Okay, so let's start with a different question. You were up first.
Well, I think we're on. Okay.
Yep.
Well, in the spirit of DARPA, challenges, complexity, my young people in my home still might say, let's get the party started, or whatever they say. But the point is, I applaud comments/questions, and I'd love your thoughts. In itself, the way you've described the problem set, it's understandable. John tackled some aspects, A2AD, Evan, you other, and down the line, control systems, computer systems. So nicely done. Because what it really alludes to, fact, is there's no one really silver bullet, cyber arrow, whatever you want to analogy. What I'd like to offer is that on some of those aspects, on the standards interface discussion, completely agree, we've come some distances. I would offer that we're probably in a little better shape than maybe was alluded to in some of those different language interoperability pieces. There's been prototypes already worked even some operationally, I would offer, that have been somewhat successful. Not to maybe the complexity and scale that we just offered in that large A2AD kind of picture you had up there, John, but I would offer we've made some progress. I would also offer that, Evan, to your point, we're always going to have legacy systems forever and ever and ever. It doesn't matter how you establish that. So back to this interfacing interoperability, we do have ability to certainly take legacy messages and languages. Now you have to have a very powerful fusion engine to drive that. But again, I think that's achievable. So what I'm getting at now is we covered all that. We're making some progress. Two thoughts. There's always bad guys out there that want to not enable that. So waveforms, self-healing, self-forming, ad hoc networking to kind of make it more difficult for the adversaries. That's one piece. If you haven't figured out, I'm a military person who's been at the tactical edge. And then I also offer that we kind of talked, I grew up as an RF baby, and I'm pretty good at it. But there's so much more in this world than just RF and those waveforms. And I'd like to have your thoughts again on other mediums of transport, pipes, and assuredness. So I know, if I can, great job on the panel. I think you captured the complexity. I'd like a little more, if you can, or your thoughts on some of the waveform development, which I'm pretty good at too, or discussing, but also on the different mediums, if you would. Thanks.
Okay, so would you take the first shot at that?
I think you're probably the
Or
most
John?
appropriate. I'd be happy to answer, but I think John is the one most qualified for this one.
I'll take a run at it. So I'll agree there has been, so to the comment about progress being made, you're absolutely right that progress has been made in that regard. I will assert, though, that in most cases where that progress has been made, it's been largely point-specific design areas where, as an example, taking cursor on target was a capability that was put out there a decade ago that really got pushed out to the edge, and there was a lot of systems that used that. However, it was pretty simplistic in nature in terms of what you were actually doing, and the adaptation among the different systems, you were limited to a really finite subset of data. So I think that progress has absolutely been made. It's just at the scale of the complexity that where all these systems are going that I think that that's really where the emerging challenge lies. Now, with respect to other means and other ways in which data can be transmitted, I think that when you look at whether it's the RF spectrum, the optical spectrum, looking at lasers, there's a lot of emerging research that allows you to look at ways in which you can move that data and move it in non-traditional ways where you use RF in some capacities and you use optical in other capacities based on bandwidth needs and other sharing. And so there's emerging research in looking at how, if you can understand, and just to Dr. Murray's point, if you take this as a feedback sensing type system, you can look at what is your network allowing you, what do you have available to move your data around, and then based on that, you start to move your data based on that availability. And so I think that there's always going to be some new waveform to move the data, and there's always going to be the bad guys trying to disrupt our waveforms. However, if you can get into that feedback sensing loop of understanding what's happening to those individual waveforms and how you can use the rest of your resources at your disposition to adjudicate where the data goes, I think we have a clear-cut way to address it.
Okay, Richard, do you have anything else you would like to add?
I'll just add one point, not directly related, but I think one of the things that's different about DoD systems is the role of adversaries, right? If you compare that to what we see in the kind of commercial world, and if you look at places where architectures and other things have worked well, I think in the commercial world they work pretty well, right? You can sort of get your operating system to do all this, but they're not quite the same adversarial environment, or the consequences of adversarial environments aren't there. And I think you see that in the waveform area as well, right? Just jamming everything, right, might be something that you decide to do because the consequences, right, to your to you if your opponent does that are bad enough. So that forces us to think about different types of tools and different types of attack modes and things like that.
Okay, let's take another question. There was somebody over here with a question.
Yeah, I had a question. It's Jeff Kralik from DARPA, STO. I'm not a computer scientist, but in terms of practical application of some of these techniques and some of the ideas, it seems that legacy systems are really important, legacy software. And anecdotally, many of you know that, a few months ago, the New York Stock Exchange was brought down for several hours, and found out that the reason for that was they decided they wanted to change merely the date and time format of some legacy piece of code and in their trading computer, and that brought the whole system down. So I can only imagine where it feels like that we're all built on this creaking infrastructure of code, legacy code, and many of these complex systems are relying on it, and it really maybe an issue that needs to be addressed is how do you wrangle complexity in upgrading legacy systems? I wonder if you have any solutions for that.
I think, Kathleen, I'd like you to take that one.
Right. One of the axioms of the Hackams program was we weren't going to worry about legacy code. We were going to allow ourselves the freedom of a clean slate because we felt like the problem was hard enough in the clean slate version to tackle it just there. But the researchers made sufficient progress in phase 1 that they started to look at legacy systems in phase 2. And so in phase 2, on the quadcopter, they had partitions where in the SCL4 was configured to have separate partitions, and in some of those partitions, legacy code was allowed to run. And so like the code that was processing, doing the camera, figuring out which pictures to take and how to, when to send them back, was all untouched legacy code. So that gives a way of integrating, at least in that case, it didn't matter what the functionality of that was doing, it couldn't possibly interfere with the functioning of the overall system. So that's a case of an exquisite artifact where you cared very much about the security. It's not an answer for the billions of lines of software out there. I think that we are moving towards a world where we're able to build critical pieces to higher levels of assurance with reasonable levels of effort. That's going to be a long process, and we're going to sort of start to go from everything's wildly insecure to some things are actually reasonably secure, and then kind of expand that frontier out. And in the process of doing that, there's going to be a lot of boo-boos where the stock exchange crashes and we don't get to the key things in time. But over time, our tools are getting much better, our levels of automation are getting much better. So eventually I think we'll be in a much better situation, but I think we're talking about 50 years. So I'm sorry that I can't, I think that we are making good progress, but it's a long slog. And there's a lot of really great ideas that are happening, and a lot of more great ideas have to happen. And that's, that's what DARPA is in the business of doing, right? Is trying to solve these really hard problems.
Okay, I think we've got another question over here.
My question is, in these complex systems, when a threat can occur at a fairly low-level node, but be very consequential for the overall system, like if in your flight test demo, for example, someone had flown in that airspace 6 hours earlier and released some anthrax, and there's some sensor on that plane that is a biosensor, not the red code team with access to the code trying to hack, but physical environment hacking. And it's difficult to verify the threat because it is that single low-level node that is your first indication that there's a problem. At the moment, I'm working in hospital administration, so I'm abstracting this to my world. So one nurse thinks she's got an Ebola patient in her clinic. To me, that's the abstraction of this example I'm giving for your plane. Is the complex system, how is it tested for that sort of a threat when verification is very difficult? And when the threats are coming from environmental challenges and not software-based challenges.
I think Kathleen.
Right. So you can reason about both the code and the environment. You can have models of the environment and what's possible and what's not possible. So you could have a specification of the system that includes the possibility of an anthrax attack or an Ebola patient, and you can reason about that using roughly the same kinds of tools and techniques that I'm talking about. But what's impossible to do is reason about things that you didn't capture. So if you took the time to think about, oh, right, this is a scenario that we care about, then you can reason about it using exactly the same kinds of things I'm talking about. If you didn't think about that, then all bets are off. Who knows what will happen? Anything in some sense could happen. So in the formal methods community, there's a distinction between something called verification and something called validation. So verification is, does your system do what the specification says it's supposed to? And a lot of the tools and techniques I've been talking about are focused on that verification problem. The separate problem of validation is your specification correct? Is it saying what you want to have happen? And does it cover all the cases that you care about? So that's an equally important problem that boils down in some sense to people, experts getting together and hashing out cases and figuring out what do we care about. And you can start to analyze if you have a specification that's in some sense executable, you can create simulations where you go through and you try out, like this could happen, that could happen, does that make sense? Is our specification saying the right thing? You can have experts look at that. But there's no way to prove that your specification is complete, that it covers all possible cases. All you can do is in some sense test the specification, have the people, the experts be able to look at it and say, yes, this covers what we care about. And then when you forget something and something terrible happens, you're like, okay, we need to add another case. And that's really what happens in life today, right? So this is just transporting it into a situation where we can reason about it formally.
Richard, did you want
Yeah,
to
so
add something?
one other thing, I think what Kathleen says is exactly right. One of the things we can also do, though, you're limited by your model. So your model says, here's the model of what the environment can do. Then what somebody should do to attack it is do something you didn't model because you didn't. But we also are in a time when we have enormous amounts of data. One of the things we don't do that we could be doing is comparing our environmental models to what we see. Right? So in others, you've got cars driving around, you've got planes flying around, you've got sort of sensing of what the electromagnetic environment is. Are the models that we're using to formally verify these things, right, matching that? And if they're not, even if the system responded correctly, you don't have a guarantee anymore, and we ought to go back and modify that environmental model and say, hey, we actually saw something that our environmental model didn't catch. Let's put it in the environmental model, make sure that there's no combination of things, which is exactly what formal methods will do for you in model checking, that could have caused a problem, even though they didn't that time. So I think we can do even more than just debugging by waiting for failure, right? We can start to look at when do our models not match, right? And then using that to update our models and then going back and asking proactively, is there some combination of things that somebody could have exploited? So that's another thing I think can be done.
Evan, would you like to add something?
Yeah, and I think you can even go a step further than that, is look at runtime monitoring of the environment and decide when your environment is sufficiently different than your assumptions of the environment. Do you have to make that trade-off of, do I force isolation to reduce complexity and the risk of cascading failures, i.e. just say, I don't know what it's going to do, so I'm just going to block it completely. I'm not going to let that sensor feed into the system. Or do I accept the risk of continuing the mission with this very uncertain environment? And by monitoring those environmental conditions, you can make those trade-offs and accept the right level of risk.
Great. I think we've got another question.
Hi, I'm Chris Taggart with General Dynamics. You'd mentioned before about the automobile industry, which has its own thousands of, pounds of metal hurtling down highways where people's lives are at stake, with very complex systems and tens of millions of lines of code in the cars. And I was actually fairly impressed by that, kind of wondering, it's a different world that they live in. But are they doing things well, handling the complexity of their automobiles with millions on the road? And is the DoD problem different? Are we learning from them in some way?
So I'll assert that the DoD problem is substantially different in the sense that every piece of information that's being produced or consumed on an airplane has a specific purpose that it's intended for. And the way in which those systems get composed has a different level of interaction between them. If you look at the complexity with, this is an oversimplification, but in a lot of cases with what you have in an automobile, it's really about a lot of actuation systems and control units that your code is centered around. Whereas with, a F-35, you've got a helmet-mounted display that's providing the ability for the pilot to have 360-degree situational awareness and understanding, how that track fuses with that track. And as the automobile industry continues to go toward the driverless car, a lot of this information fusion and pulling this information together is starting to rival what has to go on inside of an airplane, but there's still a fair amount of differences in my mind in terms of that complexity and how they come together.
Okay, are there other questions? Okay, here, we've got.
Dennis Foll from Georgia Tech. From the remarks today, it seems like complexity is a bad thing, that it has these vulnerabilities that we need to eliminate and these unintended consequences that we might realize, or these unpredictability that we need to solve. I didn't hear much about the good side of complexity and how to engineer it. It is, after all, from complexity that we get increased functionality, adaptability, resilience. So what tools and methods are you pursuing to get us to a better job of engineering complexity and getting the emergent properties that we want? Thank you.
Okay, Richard?
So I'd say a little bit about that. I think it's a great question. there's no question, I'll take a control theory point of view for a second. We always talk about the trade-offs between performance and robustness, right? And so as we try and add more performance, add more features, right, all of those things, we run the risk, right, of becoming sensitive to some of those very things. And so I think, I'll give the example of online optimization-based control. That's great. What does it allow us to do? It allows us to be adaptable, allows us higher performance, better efficiency, et cetera. But we now are dependent on the model that we use. We have to have larger computation, probably more computers, probably backup computers, probably networks between all of these things, lots more sensors. So there's always that trade-off. So I think you're right. And there certainly are, in some fields, places where you can say, okay, there's a fundamental limit here, a trade-off between that robustness and performance, but that's rare and occurs in very special systems. I think a more general theory for how do we think about the number of features versus the fragility of the system would be something that's very useful. But at least I don't know about that in the domains that I know, and maybe others know about places where that kind of formal trade-off is there, but I think you're exactly right.
And I would add that, those standardization efforts where the right types of information are being exposed, that does become part of a design process when you understand what information is going to be available and what you're going to do with that information. And so that does help. The other part of that is that through some of these standardization activities, it's actually providing a mechanism for abstraction from some of the complexity. And so in the spirit of being able to put together more complex systems, you're breaking it down into smaller problems that are more tractable for people to put together. And then as you take those problems or those components and put them together, you're actually getting something much more complex, but you were tackling it at a smaller level. So I think that there are tools in place that are trying to tackle that.
And I think either Evan or Kathleen can comment on the divide and conquer philosophy.
Yeah, and I think there are different scales where you want complexity. Complexity helps in the optimized solution in the end game. It doesn't help in the design and maintenance. What you really want to do is separate those two out and manage your design and maintenance of the life cycle in an abstracted way that protects you from the complexity, because that's where you create issues, while still keeping the performance benefits of embracing the complexity and the concrete implementations at the end. So this idea of optimizing post-design, optimizing post-composition, optimizing post your final construction gives you that benefit of both, and it's only recently that we've started to mature the tools to allow us to do this very late binding optimizations that gives us the benefit of complexities without the pain of complexity. But it's a very active field of research.
Please go ahead.
How you doing? Richard Isaac from DARPA. So I got a question for you. Interesting panel, interesting discussion, but where do you think machine learning plays into this? We start talking about wrangling complexities in the system of systems. Where do you think it can help? Where do you think it will not help? And what's a timeline for that? Because if you think about managing like the RF spectrum, what's out there, what's going to work, what's not going to work based on what you're confronted that day. Even like a helmet mounted display, customize that pilot, what that pilot has over time. It can build that and kind of project what that pilot needs for that mission. Talk about system of systems, cyber, EW, those kind of things. Where do you think it's going to go in the future? Do you think it's a good thing or not? That's what I'm kind of curious, because no one talked about that. And I think that if you talk about the amount of information, we talk about system of systems, it's going to be sensory overload. So someone has to be automated, but not just automated, so the machine can learn and actually adapt so we can actually get that warfighting effect that's out there. So I'm just curious to your guys' thoughts.
Okay, John?
Yeah. So I think that machine learning is going to play an instrumental role in putting these different systems together. Basically, going back to the whole control theory side of it, because as that information's out there and available, you're going to be sensing the environment, trying to work toward making decisions based on what you know. And when that didn't work, now what do I do next? And that got into part of what I talked about in my upfront piece, is that where we're at right now, there's still a lot of human feedback in that process. And for us to eliminate that human feedback that slows some of these systems down, that machine learning has to be brought forward as a technology that becomes an enabler. And at the same time, then validating that it's actually doing what it's supposed to do. And so I think it's an instrumental part of bringing all the complexity together, but it's very much on the early phases or early stages of development, at least with what I know about.
Right, I think there's lots of promise in machine learning in this kind of area. Like the DARPA Grand Challenge, the first version, the cars couldn't get more than a few miles out of the starting gate because the vision system was hand encoded. But the next version, they did use machine learning instead, and many of the cars were able to finish. So there's lots of potential, but one of the real challenges is understanding the scope of what the machine learning code will do. How do you know that it won't do something crazy in some case that didn't happen to get triggered? So the validation problem or the certification problem for machine learning code is a real challenge. This is a problem that researchers are studying quite a bit, and I don't know that we have a great answer. One of the approaches is the so-called simplex architecture, where you kind of allow the machine learning system to do whatever it wants as long as you can guarantee that it's going to stay within this envelope of accepted behavior. But if it starts to get close to the edge, you shut it down and you revert back to a simpler, less functional version that you know isn't going to run off the rails. So I think there's a lot of research to be done in this area.
Okay, are there any others? Well, I'm going to wrap it up with one question. And it's around, and I think, Kathleen, you just started it. Verifying adaptive or intelligent systems is a very difficult thing, as we just talked about. Or is your research looking into any new methods to help to provide the right assurance for such systems?
I think I just answered that, so maybe...
So, I think it's a great question. I think testing out systems in these kind of very complex behavioral spaces and trying to understand what they're going to do is extremely complicated. The best approach that I know how to do it is to take a model-based formal approach at the design stage when you can, try and sort of model what you think is going to happen and make sure that your system is safe with respect to that. And then layer on top of that, making use of the data that you collect to both validate your environmental models, to optimize with respect to what you've seen and other things. And still, right, there are going to be complex situations that you've never seen before, right? And what do you do about those? And you can't test them. It's no longer possible, right? I mean, even a predator you probably can't test.
Or cost effective.
Yeah, right. All of the possible things that could occur, and if this link fails, et cetera, et cetera. So the best we can do is probably to use model-based approaches to capture as much of that as we can, and then monitor and collect data and do other things. But it is a hard problem. I think it's going to get worse.
Okay, so that wraps up the session. Please join me in giving a big hand to the panelists. I think they did an outstanding job presenting some very complex ideas. So thank you all for being here, and enjoy the rest of the day.